All right, we're at section 21.6, entropy. And this might be a difficult topic to get your head around, but we'll get through it. So the zeroth law, let me dismiss this so it doesn't interfere with the presentation. The zeroth law of thermodynamics involves the concept of temperature, and the first law involves the concept of internal energy. Both temperature and internal energy are both state variables. And another state variable, the one related to the second law of thermodynamics, is entropy. Uh, and let's discuss two different concepts, a microstate and a macrostate. A microstate is a particular configuration of the individual constituents of a system. A macrostate is a description of the system's condition from a macroscopic point of view. So let's now dice and cards aren't thermodynamics, but they get the concepts across. Let's suppose that you look at a macrostate of 4 on a pair of dice. Well, you can have a 1 and a 3, a 2 and a 2, and a 3 and a 1. So there's 3 possible microstates. Now, what about the macrostate of getting a 2? There's only one microstate. You can get a 1 and a 1. So the we look at macrostates in 3 ways. Uncertainty. If we know that a macrostate of 4 exists, there is some uncertainty as to the microstate that exists because there are multiple microstates that will result in a 4. However, if you look at uh, getting a 2, uh, there's no uncertainty about that. There's only one microstate that'll get that, the 1 and the 1. So that's the first uncertainty. Choice is there are more choices for microstates for a 4 than for 2. So choice enters into the idea of entropy. And probability. The macrostate of 4 has a higher probability than a macrostate of 2 because there are more ways, more microstates of achieving the 4. So the notions of uncertainty, choice, and probability are all central to the concept of entropy. Let's look at some cards. Okay, the uh, in a 5-card poker hand, there's only one microstate associated with the macrostate of a royal flush. The royal flush of 5 spades, uh, laid out in order from 10 to, to the ace. Uh, on the right side, is uh, a particular hand called a worthless hand. It doesn't have any value in a 5-card poker hand. Now the likelihood of drawing the royal flush of all spades is very low probability, but the probability of getting a worthless hand is very high. Um, okay, so suppose you select 4 cards at random from a standard deck of playing cards and end up with a macrostate of 4 deuces. How many microstates are associated with this macrostate? Well, since there's only 4 twos, there's only one. There's only one microstate that'll satisfy this. Now, suppose you pick up 2 cards and end up with a macrostate of 2 aces. How many microstates are associated with this macrostate? Well, the answer is 6, and I've shown you why. You can have a spade and a club and a diamond, a club and a heart, a club and a spade, or you can have a diamond and a heart, a diamond and a spade, or a heart and a spade. Those are all the 6 ways that you can have it. So, in the if you end up with 4 deuces, there's only one. That's only one microstate. But if you end up with 2 aces, there's 6 different microstates that are associated with this macrostate. Okay, entropy. Let's talk about entropy from the dice and cards aren't thermodynamics. So let's look at it more from the section of from the idea of molecules in a room. So uh, if you look at your room, let's consider all the oxygen molecules in the air in your room located in west half of the room and um, all the nitrogen molecules in the east half. That's not very likely. Now let's, configuration 2 is the air molecules are distributed uniformly throughout the room. And configuration 2 has a higher uncertainty as to where the molecules are located. They could be anywhere, not just in one half of the room, according to the type of molecule. Configuration 2 represents more choices as to where to locate molecules. It's a much higher probability of occurring, and it represents a higher entropy. All the oxygen molecules in one half of your room and all the nitrogen molecules in the east half would be very low entropy. It would be very ordered. And this book doesn't use the term disorder, but higher entropy means a higher state of disorder according to some textbooks. They avoid it in this textbook, and I'm not sure why. Okay, let's look at macrostates and macrostates and probabilities. Um, the uh, the if you can comparison between probabilities for various microstates involves relatively small numbers for dice and poker hands, but uh, the macroscopic thermodynamic system having approximately Avogadro's number of molecules, the ratios of probabilities can be astronomical. Let's consider just 100 molecules in a container. Half the molecules are oxygen and the other half are nitrogen. At any given point, the probability of one molecule being uh, in the left of the container and figure A on the top as a result of random is 1/2. If two molecules, the probability of both being in the left is 1/2 squared, 1 in 4. Okay, if we look at here, you have a half. Here, there's 1 in 4. I mean, it's um, in the left. There's only this one, so that's 1 in 4. Three molecules, it's 1/2 cubed, that's 1 in 8. See, this is out of these 8 configurations, this is the only one that has all 3 molecules in 8. Now, for 100 independently moving molecules, the probability of 50 oxygen molecules in the left part at any moment is 1/2 to the 50. The probability that the remaining 50 nitrogen molecules in the right part at any moment is 1/2 to the 50th. Now, the probability of finding this oxygen-nitrogen separation as a result of a random motion is 1/2 to the 50 times 1/2 to the 50 equals 1/2 to the 100. So it's the probability is like 1 in 10 to the 30th. So when calculation is extrapolated from 100 molecules to the number of in 1 mole of gas, 6.02 times 10 to the 23 molecules, the separated arrangement is extremely improbable. So that's the end of that section, end of 21.6. We'll go on to 21.7, entropy in thermodynamic systems.